Hi everyone, welcome back to Chem Story. Today we're jumping into an important reaction that involves alkynes, catalytic hydrogenation. We'll take a look at how alkynes react with hydrogen gas, and depending on the conditions, what kinds of products we can actually make. It's a really useful transformation when you want to either build up or break down a molecule, so let's get into it. Let's start with the basics. When we say catalytic hydrogenation of alkynes, we're usually talking about full hydrogenation, turning an alkyne completely into an alkane. To do this, we use hydrogen gas H2 along with a metal catalyst like platinum, palladium, or nickel. The triple bond gets reduced in two steps, first to a double bond, then to a single bond. The reaction happens so fast, it skips right past the alkene. We don't even get a chance to see it. You can see that in the reaction scheme. We start with an alkyne, add hydrogen with palladium on carbon, and we end up with a fully saturated alkane. So the big idea here is, this reaction is a very efficient way to make alkanes. Mechanistically, this reaction goes through synaddition, meaning both hydrogen atoms add to the same side of the molecule, either both from the top or both from the bottom. As the reaction moves forward, it goes from a triple bond to a double bond, and then all the way down to a single bond. Now technically, a cis-Alkene does form along the way, but the thing is, the reaction doesn't stop there. That intermediate just keeps going and picks up another hydrogen right away. So in practice, we almost never see the cis-Alkene on its own. What we actually see is just the final product, the fully saturated alkane. Now, what if we don't want to go all the way to an alkane? Sometimes, we actually want to stop at the alkene stage, more specifically, at a cis-Alkene. To do that, we need to slow the reaction down and have a little more control over it. And the way we do that is by using a less reactive catalyst. Instead of using regular palladium or nickel, we use something like the Lindlar catalyst. This setup allows the reaction to stop at the double bond, so we end up with a cis-Alkene. So it's still the same hydrogen gas, but by switching to a modified catalyst, we're able to pause the reaction at the alkene stage. Let's take a closer look at the catalyst itself. The Lindlar catalyst is basically palladium, but it's been poisoned. Now that might sound a little odd, but in this case, poisoning just means we've made the catalyst less reactive on purpose. We do that by adding things like lead acetate and quinoline, which blocks some of the active sites on the metal surface. Then the whole mixture gets supported on something like calcium carbonate or barium sulfate. Another option is P2 nickel, which you can make by reacting nickel acetate with sodium borohydride and alcohol. Just like the Lindlar catalyst, it also slows down hydrogenation, so the reaction stops at the cis-Alkene stage. If you take a look at the energy diagram for this reaction, it really helps you see where the selectivity comes from. On this reaction coordinate diagram, you can track how the energy changes as we go from an alkyne to an alkene and finally to an alkane. Now focus on the yellow box on the left. That part shows the first step where the alkyne gets converted to the alkene. When we use a poisoned catalyst like the Lindlar catalyst, this step is catalyzed, so it happens pretty easily. But now look at the green box on the right. This step is not catalyzed. That second step, going from alkene to alkane, doesn't get any help from the catalyst. So without that extra boost, the activation energy stays high, and the reaction just stalls right there. That's why the whole thing stops at the alkene stage. If we were using a regular metal catalyst, both steps would be catalyzed, and the reaction would go all the way to the alkane. But with a poison catalyst, that second downhill slide is blocked, like hitting a roadblock in the middle of the path. And that's exactly what lets us stop the reaction at the cis-Alkene and actually isolate it as the final product. So far, we've looked at how to make alkanes and cis-Alkenes from alkynes. Now let's check out one more route, making trans-Alkenes. To do that, we use a totally different method called dissolving metal reduction. In this reaction, we treat the alkyne with sodium metal in liquid ammonia. And what we get is a trans-Alkene, where the two hydrogen atoms add to opposite sides of the double bond. Let's break this down a little more. The key to this reaction is electron transfer. When you dissolve a metal like sodium or lithium in liquid ammonia, It releases free electrons into the solution. Those electrons then get transferred to the alkyne, and that's what kicks off the reduction process. The alkyne picks up those electrons and slowly transforms into a trans-Alkene. And it's not just sodium you can use. Other metals like lithium, zinc, magnesium, or iron can also do the trick. But in practice, it's usually the alkali metals, sodium and lithium, that are most commonly used. Let's take a closer look at how the dissolving metal reduction works, step by step. We start with an alkyne, and when sodium donates an electron, we form a radical anion. That radical anion then grabs a proton from ammonia, turning into a vinyl radical. Next, another sodium atom comes in and donates a second electron, giving us a vinyl anion. That anion picks up one more proton, and just like that, we get our trans-Alkene. The whole thing moves through radical and anionic intermediates. And the key here is the geometry of those intermediates. They naturally arrange themselves so that the hydrogen atoms end up on opposite sides. That's what gives us the trans configuration in the final product. Let's wrap things up by comparing all three methods side by side, using a real example. If we do full hydrogenation with palladium on carbon, we get hexane, a fully saturated alkane. If we want to stop at the cis-Alkene, we use the Lindlar catalyst and we get cis-hex-3-an. And if we're aiming for the trans-Alkene, we use sodium and liquid ammonia, which gives us trans-hex-3-an. So depending on which product you're going for, alkane, cis-Alkene, or trans-Alkene, you just pick the right set of conditions. And that's the beauty of selective catalytic hydrogenation in organic synthesis. All right, that brings us to the end of our lesson on catalytic hydrogenation of alkynes. We looked at three different pathways: complete hydrogenation to alkanes, partial hydrogenation to cis-Alkenes, and dissolving metal reduction to get trans-Alkenes. Each one works through its own mechanism, and each gives you a different product depending on how you run the reaction. Thanks so much for watching, and as always, I'll see you in the next Chem Story video.